Okay, so we're discussing this idea of conditional expectation or conditional mean being the best predictor. So if you have a random variable y and you want to predict it based on x, um, so you can form a general function of x, let's say g of x. So you don't observe y, you observe x, you want to predict y. A natural thing is to form a general function of x. And then you measure the prediction error, um, which is y minus g of x, in mean a squared sense. So you square it and you take the expectation. So this gives you a number. And so you can score different predictors as you vary g. And the point here is there's a decomposition of this, you can call it risk or error, in this format. And here m of x is the conditional mean. Okay, so the conditional mean of y given x. And so this part does not depend on g. This one we did last time. We proved it, and is a consequence of the fact that the residual of conditional mean. So your conditional mean is a function of x, so it's a candidate predictor. The conditional mean of that residual is zero, and this leads to this decomposition. So this term we can't optimize over. If you want to like choose g, this is constant. This part we can make it zero if we choose g equal to m of x, and if it's not equal to m of x, this is going to be non-negative always. So any choice of g is going to do at this as the mean is squared, sorry, the conditional mean. And so the conditional mean is the best predictor. So it's the one that minimizes this. So it makes this term zero. Okay. Is this kind of clear? This is a very important concept. This was a little bit fast towards the end of the last lecture, but I encourage you to go through the proof. The proof basically relies on uh, this is some sort of an orthogonality if we get to it. So it's like saying the residual kind of is orthogonal in the expectation sense to the difference of the two estimators or the predictors. Um, so the point is, this is for a general class of G. If I restrict myself to the class of constant functions, I argued last time that that would give you the usual expectation. Another class is a linear class. So this subsumes kind of the constant predictor. So if I restrict myself to the linear class, I can say what happens if I try to minimize. Let me write it down here. I want to minimize the prediction error, the average prediction error, the MSE, over G such that G is linear. Okay, or rather it should be like affine. It's more precise, is affine. Affine means a function that looks like this. So you get a constant plus b of x. It would be linear if this is zero. Sometimes you call it linear. Um, but if you want to be very precise mathematically, it's really an affine function. So restrict attention to affine functions. Um, this solution may not be conditional expectation. So we did an example last time. So in this example, the conditional expectation turned out to be quadratic. It's a quadratic function. So if I restrict myself to linear functions, it's not going to give me like the best linear predictor is not going to be this. And it turns out in this case, the best linear predictor would be actually a constant function. But we want to find the best linear predictor. What we can do is we can try to minimize this over such functions. I just plug in. So I need to minimize. We can minimize instead this general form. So I plug in the form minus a minus bx squared, right? And then minimize over a and b. I just need to find the a and b, right? There are different ways of doing this. one thing is like you can try to expand this and then you get like a um, polynomial like degree 2 in A and B and you try to differentiate. The um, the other thing is like you could simplify your life a little bit by doing a centering. So what happens is that I can kind of decouple. Um, so let's try. If I add and subtract, for example, suppose I add and subtract minus a plus expectation of x minus b, or actually there's going to be a b here, and plus b expectation of x, and then minus b expectation of x. Add and subtract this piece. Right, this is going to simplify our life. Um, let's take this and this together. So, and then the rest I'm going to write here. So y minus a minus b. Uh, yeah, minus b. And then plus, or rather, let's do it, minus b x minus expectation of x. Okay, so that's that. Um, let me know if it wasn't correct, but I think the first would give me that term, the second would give me this term. Now what I'm going to do is I am going to call this x tilde. If you remember, this is kind of a notation that we had. It's like the centered x, so this is zero mean, a zero mean. Um, and uh, this, yeah, I want to also do, I want to also add and subtract basically expectation of y. So I'm going to add and subtract expectation of y as well. So I'm going to get minus a minus b. Hopefully it's not going to be problematic. So I'm going to add, subtract expectation of y. So this is going to be y tilde as well. Um, now this thing is a constant, right? Um, and what happens is, uh, so these two are zero mean, right? So if I, okay, there's a b here somewhere. There should be a b here. Okay. Um, so imagine calling like y tilde plus bx tilde some z tilde, right? So this is still zero mean because these are zero mean. And for any b, by linearity, the expectation of z would be zero. So this is really z tilde plus c squared. So if I expand, what I get is the expectation of this squared plus c expectation of z tilde 2 plus c squared. Okay. And if I want to minimize this, first note that um, the expectation of z is 0. So this is 0. Okay. So I have to, like, this c is a function of both, and this one just only contains b. So this contains only a. So when I try to minimize this, let's say over a, it involves only this, and the way to make this 0 is to make c equal 0, because it's like both of them are non-negative. So minimize over a, it implies that c has to be 0. I mean, you could have done it like by just differentiating, but this is easier. So this implies c equal to 0, which means this has to be 0. So it has to, we have to have this equation. So a has to be expectation of y minus b expectation of x. Okay, so if you minimize over a first, this term doesn't depend, so it only depends on uh, A and B, this only depends on B. Okay, so the first thing that we do is minimize over. Uh, sorry, let me grab this. Let's see here, sorry. Uh, okay, I'm gonna add. Okay, yes. So minimize over A implies that C is equal to 0, so it gives me um, that expectation of Y has to be, that A has to be expectation of B, sorry, Y minus B expectation of X. Okay, it gives me this equation. Okay, so if I know B, then A is defined like this. So basically what we ended up doing is that reduce the problem to the centered case. So this Z involves the centered case. So we're minimizing now. So minimize over B now. This is equivalent to minimizing this part. Okay, over B, which is minimize over B. If you recall what this was, the definition is here, would be equal to like minimize expectation of Y tilde plus BX tilde. Right, so now you'd get minimize, you expand. So you get expectation of Y tilde plus 2B expectation of X tilde Y tilde plus B squared expectation of X tilde. Okay, minimize over B. So now anyone can tell me what each of these terms are. So what is this? What is this? And what is that? Anyone? So reduce the problem to the centered case. We could have from the start assumed that X and Y have zero mean. Um, so A was going to be like just determined by the mean of the two, but B is the interesting coefficient here. Anyone knows what these are? What is the expectation of Y tilde? Y tilde is the centered version of Y. Anyone? What is that? Can you hear me? Any one of these terms look familiar? This is variance of Y. How about this? This is variance of X. How about the middle term? This one. Yeah. So this is the covariance of X and Y. Good. Two people. So if I want to minimize, this is a quadratic function in B. So these terms are like variance of Y, covariance of X and Y, and variance of X are constant. So if I want to minimize, I can differentiate and set to 0. You get 2B cov X and Y plus 2B okay. You can see there's a mistake here, so there's a minus sign. So this should be defined as minus. This should really be minus. So then I get minus here, 2B variance of X. So set equal to 0, this implies that B has to be, the optimal B has to be cov xy divided by the variance of X. Okay. And so this really, I mean, can verify that this really minimizes. So if I choose A like that and B like this, then I first choose B like this and then A set it equal to that, then this estimator would be the best predictor, the best linear predictor. So this is like really the population level regression. If you've seen regression, this is like simple linear regression. You're trying to minimize this. This is really simple linear regression, but in population form. So there's an expectation here. In practice, you like observe samples, and then this would be like a finite sum, like a weighted average. Sorry, not weighted, just the empirical average. But this is the population regression. So you if you check, you've seen probably simple linear regression before. So you check, this is like you'd see something like xi, yi, where xi minus x bar times yi minus y bar, and then divided by summation xi minus x bar squared. This is really, if you divide by 1 over n, as n goes to infinity, these are really this kind of situation. Okay. It's a clean population overflow. So this is going to be the best linear predictor. And then you can verify just as an exercise, if you look at the minimum error, the error that you achieve is like something like this, or rho squared is like the uh, correlation coefficient. So this is like the population version of regression line. In 100C, you'll see, or like before you've seen it in 100C, again, you'll see the sampled version, and this can be done for any joint distribution, but it might not be the best predictor. It's like the best linear predictor. Okay, and then any questions about this derivation? It was a little like more complicated than the more general case. The more general case turned out to be even simpler. And this example tells you that these are generally different. So in this case, if you do it, you can see B, basically the covariance is 0. So that B, which is like, let's call this B hat, would be covariance of xy. The slope of that line would be 0 in this case. So really, you'd get to the flat line. In general, it would be a general line, but then you can see the best linear predictor, which also the best constant predictor, is doing much worse in terms of prediction than the best predictor here. Anyways, these are very interesting. If you don't understand, let me know. Let me come to office hours. But I'm gonna move forward. Just maybe pause a little bit. If you have questions, let me know. Otherwise, is this clear? Best linear predictor versus best predictor in general in the MSE sense. We now have both. Um, so if you do have a jointly normal distribution, and if you write down the joint density, then you can write down the conditional density of y given x. And it will turn out to be like this. I'm not going to do it here. I mean, at some point in your studies, you would do it. But it requires you to write down the joint density and then the marginal density and then just divide and simplify. So the conditional distribution is still going to be Gaussian, but the means and the variance would change. And you can see the mean here. This is really the conditional expectation of y given x. This is the best predictor of y among all functions, but in this case happens to be linear or like affine. You can see it's like, you can write it in this fashion, mu of y minus, if you call this b hat, minus, or yeah, minus b hat mu x, which is really that a hat that we had. And then b hat is really rho sigma uh, this doesn't seem to be correct. Yeah, it's actually correct. So you can write it in terms of this. In terms of the rho, this thing you can also write it as, this is rho sigma x squared sigma y squared. This is sigma x squared. Sorry, covariance is not the squared, sigma x, sigma rho, sigma y, and so it simplifies to rho sigma y divided by sigma x. That's another thing in terms of the correlation coefficient. So this is really the same formula here. So it turns out that the best linear predictor and the best predictor just match. So the best predictor would be linear predictor. This is a special case of so this VD is this quantity. This thing is really a hat plus b hat x. So it's really saying that the conditional expectation is linear and it just like coincide. The best predictor and the best linear predictor coincide in this case. And this also like it really matches this. Okay, it's the variance of the residual, like the unpredictable part. Okay, so the best conditional mean is exactly the best linear predictor. This is that statement here. The conditional variance does not depend on x. This is true in general for the residual, like in linear regression. But for a general case, when you have like the conditional expectation, the conditional variance could depend on x, but in this case it doesn't, and it's reduced by this factor. You can see like compared to the marginal variance of y, if they're correlated, this rho squared would be larger than 0, so you decrease the variance of y. So you predict it by x. If there's correlation, you're successful a little bit and reduce the residual variance. Okay. Basically, like the conditional mean, you have to like graphically go and look at the center of all of these, and the centers like lie in a line. It's kind of the visual representation. Okay, sounds good. So this one I'll let you do as an example for yourself. So this is an example where like z is a hidden variable, and then you're measuring it. So x, this is what you observe is like this hidden latent variable plus noise. Both of them are Gaussian and they're independent. They have different variances. And so if you do this calculation, compute the conditional expectation of z given x, you can use this formula. That would give you this quantity. And you can see it's like some sort of a shrinkage. This is less than 1. So you would shrink the value that you observe because you know that it's noisy. So you predict it to be, predict z to be in general smaller. And then this is going to be the conditional variance. So this idea is called shrinkage. So noisy observations will pull back towards the prior mean. This you can think of it as a prior. Yeah, the prior knowledge that this is centered at 0, and this is saying x given z equals z is like normal, it means z, little z, and variance sigma squared. So this is the likelihood part, basically. And there's going to be a posterior. So posterior would be the distribution of z given x. So you observe this is the likelihood. If you go back to our discussion, this is like the likelihood, this is like the prior distribution, this one. And then there's going to be a posterior, this is going to be normal with this mean, and the variance you can compute, which is going to be this. So there's a posterior information would be, once you observe x, how can you predict z, the unknown? And this is how you do it, okay? So more measurement noise means more shrinkage. So if you have more of this would be smaller. If you have more variation than prior, this would be larger, so they would shrink less. So this quantity, yeah, is many things. So it's like both the best, it's like the conditional expectation, It's also the least squares predictor, or the best predictor in this case, and also it's the Bayesian posterior mean. So posterior here would be the distribution of z given x, and it's the mean of that distribution. Okay, so this example contains a lot of kind of concepts together. So it's like the Bayesian um, approach where you have a prior, you have a likelihood you observe something conditional on the unknown variable. Then you can form the posterior, which is the distribution of the latent or unknown variable given the observation. The posterior has a mean. In this case, this mean is going to be the best uh, predictor in the MSE, or at least the squares refers to the condition. It's like we're minimizing the square of the error. So least squares refers to that. So least squares estimator, the best linear least squares estimator, the best general least squares estimator is also the conditional expectation. Okay, sounds good. I'll let you think about this example. It's very important, kind of very simple, but this is kind of the essence of um, Bayesian approach. So, and you can think of the what we discussed. This is the best predictor is really the mean of the posterior. If you imagine y is something that you don't observe, and x is something that you observe, and then you try to predict y based on x. Here's z is like that. There's kind of some relation. There should be some relation between them for you to be able to predict z based on x, and this is the simplest case. Okay, so we talked about conditional expectation as a random variable. This is important. And then we talked about the fact that the residual has conditional mean 0, and this is a like foundational observation. It just everything follows from that. Talks about Adam's law, Eve's law, which is the like a decomposition of the variance idea. Uh, talked about basically mixture models, if you remember. Talked about the fact that this is the best linear predictor, and talked about the case where you have jointly normal variables in which the best predictor and the best linear predictor kind of match. Okay, any questions about this? You're done with this. Any question about conditional expectations? It was a very important lesson, like lecture, and I encourage you to go through and kind of understand everything in that lecture. We did a lot of basically visit a lot of concepts. And now you can do like once you understand that lecture, you can do a lot of interesting stuff. Questions, comments? No comments. So if not, in the next two lectures, I want to talk about like these important limiting results. And today and the next lecture, basically about CLT is really important. So today is about concentration, this idea of concentration, sometimes called concentration of measure, or another way of saying it is why averages work, and is central to the effectiveness of statistics. Okay, so we talked about expectation, and we mentioned kind of that this expectation is related to the long run frequencies, but we really didn't kind of prove things. So today we're gonna kind of prove, we basically discuss this at some point briefly. But suppose you have IID observations with mean, mu, and variance sigma squared. So these are like random variables. They can be discrete, they can be continuous, or it could be like more general even. So you have a sequence of them, let's say n of them, and they're IID, so identically distributed and independent. So independent, identically distributed. So independence is really key here. If you form the average, this is like an empirical average. Suppose you observe these, each is a random variable. So you can form this average. And we did some calculations. So the expectation would be the expectation. So each one has the same expectation because they're IID. Expectation of x1 is the same as the expectation of x2. all the way. And so this common value is mu. They have is the same distribution. So there's the single mu and the same variance. So the same variance is sigma squared. So if you look at the expectation of x bar, we calculated it using linearity. Expectation would be mu. And we also did the variance of x bar, and it turned out to be sigma squared over n. Anyone remembers how this turns out to be sigma squared over n? Let's see if you remember. How can I prove something like this? Anyone? Variance of x bar n, to remind you, is variance of 1 over n summation I from 1 to n xi. So why is this equal to? Use the sample mean definition. Okay. Before I do the independence, I'm going to do like I pull it out, I get n squared. Then I have the variance of the sum. And I note that this in general is not equal to the sum of the variances, but in this case, because of independence, they're all independent, so we can write it as the sum. Then what? What is the next step? I get 1 over n squared summation I from 1 to n variance of xi. This is by independence. How can I simplify further? What are these things? They're identically distributed. Yes, so each one would be sigma squared and doesn't depend on I. So this whole thing would be n times sigma squared. And one of the n's cancel. So I have n squared on the denominator. So this gives me sigma squared over n. And so this is the key fact that the variance of the average, so the average, the empirical average, so you can call it empirical average, has the same expectation or mean as each one of them, but the variance of it is much smaller. As n grows, this goes to 0. Okay, so this converges to 0. As n goes to infinity, and we discussed this is really the essential idea of concentration. If you imagine um, the distribution x bar n, you're not assuming anything about the distribution, but it has the same center, but it gets sharper because the variance gets smaller. You'd end up having more peaked, like you'll have a more peaked distribution. So as you increase n, it peaks around the value because the variance is smaller. And this is kind of what we want to kind of formally prove. Okay, we want to formally say that basically the majority of the mass is going to be concentrated. Probability mass will be concentrated around mu. Okay, and this is the context of the law of large number. The way to characterize it is to look at the probability. So if you imagine mu, if I look at an interval around mu, I can characterize this concentration by saying how much probability is assigned to this interval. How much probability mass we have. If this is growing, then it means that this interval becomes more and more probable. So it's much more likely, for example, to find the average here for n equal like 100 relative to a 10, and much more likely if its n is 1,000. So if this turns out to be approaching, so the probability that x bar n lies in this interval will show that this approach is 1. In other words, the complement, which is, so this you can write it as the same as x bar and minus mu. Norm of it is less than or equal to epsilon. Okay. Let me write it like this. Open interval. Doesn't matter for continuous variables. And for not continuous variable also doesn't matter, but for simplicity. So the probability that this is less than epsilon, the deviation of, so this interval x bar n lies in this interval if and only if the distance of x bar n and mu is less than epsilon. So this is what we're going to show is that this goes to 1. Alternatively, this is the complement of that event. So if you look at this event, if this is A, this is A complement. So the A complement, this is going to go to 0. Okay. And we're going to characterize actually how large n needs to be for this to be less than a pre-specified value. Okay, but the fact that this converges to 0 is the so-called law of large numbers. Okay. Um, does this make kind of sense? It's not that obvious the first time you see that this is the right quantity to look at, but the probability we assign to basically outside this interval. So what that interval is like this is x bar n minus mu, bigger than epsilon. The probability that you assign there is going to be getting smaller and smaller. Okay, it's if you imagine these, if I fix an interval around mu, more and more of the mass is going to be inside this interval. And so the probability of that interval, fixed interval, is going to go to 1. Anything outside the probability going to 0. And this is going to hold for any fixed epsilon, which is very like interesting. So epsilon, you can take it to be any positive but small value. And as n goes to infinity, this is going to go to 0. So this leads to a bunch of interesting results. The way that this works is another way of seeing it that we'll see is like by noticing that rather than looking at x bar n, I can look at the Sn, the summation I from 1 to n. So x bar n is really Sn divided by n. Okay, I can look at this. The same phenomena happens here because if you have like, imagine like xi's are plus minus ones, okay? If they're deterministic, in the worst case, all of them are ones, and so the sum grows like n. If all of the xi's are 1, at the worst case, if you have like n is 400, this is going to be the sum with you 400. But if they're, let's say, Bernoulli, not Bernoulli, but like -1 plus 1 with equal probability, they're random and they're independent. When you add this, you get kind of something which is called a random walk. So at each point, you like Sn plus 1 would be Sn plus xn. So whatever you have, you add either plus or minus 1, and you can just plot them as a function of n. And these are the trajectories of this random walk. Each one of them is one trajectory. And you can see it just fluctuates up and down, but it's going to stay between roughly root n and minus root n. This is kind of, or a multiple of this, basically. Maybe let's say 2 root n, because this is going to be Gaussian, let's say. Minus 2 root n, like a majority of these paths would stay in this kind of parabolic shape. And the idea is you can easily show this. We already seen the variance of this would be n times the variance of one of them, which is sigma squared. So the standard deviation would be really root n times sigma. Okay, the sigma would be the variance of one of these. And so the standard deviation grows like root n. Okay, that's this kind of this root n behavior. And so it grows much slower than, rather than growing like n, it grows at worst like root n with high probability. So this allows you to, because of the like kind of stochastic cancellation, allows you to get like a much better estimate if you divide by n, because this kind of um, grows like root n when you divide by n. It goes to 0 here, like the mean is 0. So this converges to 0. Okay, this is another view via the sum. Yeah, so this is just a simple calculation. You can do it with the sum, or you can do it with the average. So the average would be um, yeah, you could do it like in this case, the things would be zero, but in general, you'd subtract the mean. So look at the xi minus mu, define Sn to be the centered sum, and the expectation would be zero. You can prove it easily by um, linearity. The variance, again, would be the sum of the variances. The mu you can drop here because the variance doesn't, it's going to be the same as the variance of mu. Sorry, the variance of xi is invariant to shifts, and you get n sigma squared, so its standard deviation would be sigma root n. So this is in general, if even if the random errors are not zero mean. So that confirms the root n a scale, and then the average minus mu would be Sn divided by n, uh, and the standard deviation would be sigma over root n, and this thing is going to zero. So this is another like view. It's just not very different than x bar n. Okay. So the main point is really like this. If you imagine the mu here is the signal part. Another way of doing it. Let me write it like this: x bar n. You can easily show that if you do a sum, this like Sn would be summation xi minus n mu, right? And then if you divide it, so you get Sn divided by n is 1 over n sigma xi minus mu. So it's really x bar n minus mu. So this is just rearranging that identity. So if you look at this is the same as this. And this is really saying x bar n is mu plus Sn over n. So this is the signal part, and this is the noise part. And this is going to zero because this is the centered sum. This is going to zero. Going to zero at a rate 1 over root n. Because the standard deviation of it is root n. This is another way of saying that standard deviation of x bar n is sigma squared over n. But you can see the signal remains unchanged. The noise kind of shrinks. Okay, this is really just another rewriting of this fact. You don't have to worry too much. But sometimes you can write it in terms of the sum and look at it a little more clearly. Any questions so far? So far, things should be kind of standard. Um, uh, okay, so before proving kind of the statement of like a law of large numbers, it is important to note that this like the expectation, sorry, the independence matters. So if things are not, so this is for example, this case happens because xi's are independent. If they're not independent, so consider this example. So xi's, let's say, have variance sigma squared, and each distinct pair have correlation rho. Okay, so this is saying correlation of xi and xj is rho, and rho is positive. Let's say rho is positive for I not equal to j. Then if I write down the variance of x bar, if I write down the variance of x bar n, what I get is that 1 squared I get again, you get the summation I from 1 to n, variance of xi. This one, sorry, this is not correct. I get the variance of summation xi, I from 1 to n. Then I have to expand this in the general form. If you remember, there's like, this is going to be summation I from 1 to n, variance of xi plus summation over all I not equal to j. This is a double sum, basically. Covariance of xi, xj. Okay? So how many pairs are there? They're going to be n squared minus n. So it's like really a matrix minus the diagonal. And all of them we're assuming to be rho, or like rho times basically sigma squared. Okay, it's really rho times sigma xi, sigma xj, but they have the same sigma, so you get sigma squared. And this is really sigma squared. So what we get is 1 over n squared. N sigma squared plus n squared minus n times rho sigma squared. So if I pull the sigma squared out, I get the sigma squared over n here, but here I'm going to get n plus n squared n times rho. Okay, and then n's kind of cancel. You get sigma squared 1 plus n minus 1 times rho, right? So do this calculation, you end up with, oh, sorry, there's a mistake. Sorry, this is n squared. So one of the n's cancel, so I get this. Right, so there was the n squared here. I have the n squared, and then one of the n's here cancel, I get this. Okay, so this is a more general form. So you look at this, we proved something like this. If rho is 0, we get back sigma squared over n. But in the worst case, this is another rewriting it. I can rewrite it by, they get n times rho here, and then divide by n, you get rho, and then you get 1 minus rho divided by n. If rho is positive, this is going to go to 0, but then this is going to converge to sigma squared rho if rho is positive. So the variance does not go to 0 and stabilize it. So this is the case where you have huge dependence. And so this is the situation where you have independence. This is plotting the, let's say, under the Gaussian assumption, the plotting the distributions. You can see for n equal 1, you have your flat, n equal 10, it sharpens, and n equal 50, like much more concentrated. Here, kind of the same situation, but rho is like 0.6, and so they kind of stabilize. The variance that stabilizes sigma squared rho, and it's slightly better, slightly less variable than the initial, but it doesn't really concentrate. So this shows that, so in this case, because correlation is positive, they're not independent. So this concentration doesn't happen. The variance doesn't go to 0. So this is really key. And like people are really interested in under what conditions this would hold. So in this case, for example, the reason why this doesn't hold is that you have all the off diagonals are rho squared, so it contributes a lot. If you had a bunch of correlations, it still would work. So this we could potentially assign as a homework problem. Um, but this is a very example of a very severe like set where every pair has the same correlation. And so in this case, you wouldn't expect a law of large number to hold. And if you look at the average doesn't lose its variability as n grows. A little bit, but not by factor of rho, basically, but not much. Is this like slide clear? This part I encourage you to prove. I did a quick proof here, but if it wasn't clear, just go through. We had the formula, general formula for the variance of the sum in terms of the covariances. And so you just write this down and then do the calculation, and this comes out. Question? So this is important. And now let's go back to the first question that we asked. Can we kind of characterize this probability concentration in terms of the probability mass basically that is outside that interval shrinks basically to 0. This one we can prove if we use a particular inequality, which is called the Markov inequality. How many people have seen the Markov inequality? Markov inequality. Have you seen Markov inequality? Potentially not, because you potentially have not seen much probability before this course, I presume. Anyone has seen Markov inequality? Okay, no. So it's a very important inequality in in a lot of areas of theoretical statistics and probability. Okay, so it concerns a random variable which is non-negative, and you have kind of parameter A which is deterministic. we want to control the probability of that the x is bigger than or equal to a. Okay, this is like a tail probability. So we want to basically calculate what is the chance that x, so x is going to be always in this part of the real line, but what is the chance that it's here? And oftentimes you care when a is kind of gets large. That's the tail. Usually for distributions, they have to go down. So as it grows, this is going to have to shrink. People like random variables can't put mass at infinity. But can I get a bound on this without assuming anything? Basically, that's the idea of Markov. So once you understand it, it's very useful. So what we can do is we can write a bunch of inequalities. The first thing is that if I have two random variables that are always satisfy an inequality, then the expectation, I can take expectation of both sides. So expectation is monotone. This is one of the properties of an expectation. Expectation is monotone. Is a monotone operator. You already know that it's linear. This is the second most important property, which is it's a linear monotone operator. And this follows just from the fact that if you have a z which is non-negative, then the expectation has to be non-negative. So imagine what this means, because so if you have this, then this follows by taking x. So this follows from, so let's call this 1, call this 2. 1 implies 2 from linearity. Take z to be x minus y, and then use linearity. Okay, so the monotonicity is really this property. And this follows if you remember what the expectation is. So expectation basically, imagine you have a discrete random variable. The expectation is for a discrete variable is really like the values it takes times the probability that it takes those values. And if the random variable is non-negative, which is this thing, always non-negative, these values are going to be non-negative. The probabilities are non-negative. You multiply them, they're going to be non-negative. You sum them, they're going to be non-negative. So it's just, for sure, the expectation is non-negative. It follows from the definition. Okay? So this is clear. So expectation is a monotone linear operator. This monotone is property 1, or that inequality. So if you remember this, you kind of go far with expectation. It's a monotone linear operator. Basically, the monotone part means I can take expectation of both sides of an inequality. Okay, this is an example that we're doing here. Okay, why this inequality holds? Because I can always write x is bigger than or equal to x times the indicator. This is an indicator variable. Okay, this is some other variable. You can think of it as just some sort of like a y. Okay, this is an indicator variable. What it says is, so what is indicator of x bigger than or equal to a? Should be a. It's just the same meaning as before. This indicator notation is saying this is a random variable which takes value 1 if x is bigger than or equal to a, and 0 otherwise. Okay. That is what this random variable is. If you remember, we talked about indicators of sets, but I mean, this is also a set, but maybe the sets were subsets of the sampler space. Here, the subset is really a subset of the sampler space, but written. Remember, this is really, if you want to, this set is, if you call this set A is really the set of all omega such that x omega is bigger than or equal to A, but we don't really worry about the sampler space, but if you want, it really is an example of those indicator variables. Okay. So this is defined I can unpack it, but let's not worry about that so much. Um, this inequality always holds, always. Anyone can see why this inequality always holds. X is always bigger than X times the indicator of X bigger than or equal to A. Can anyone tell me why this is true always? There are really two cases. Either X is bigger than or equal to 0 or not. Sorry, bigger than or equal to A or not. Anyone sees why this is true? Just consider the two cases. Yes, comes out to X bigger than or equal to, yes. So either X is bigger than or equal to A, in which case you just get X less than or equal to X because the indicator would be 1, which is true, or X is less than A, in which case the indicator is 0. This comes out as X bigger than or equal to 0, which is true by assumption. Okay, so in either case, this inequality holds. So this always holds. Because this always holds, this side is some general random variable. This is another random variable. I can take the expectation of both sides by monotonicity that I mentioned. So just take this expectation of both sides. Okay, this we have. The next stage is I can replace X here by A. I get another lower bound. Anyone sees why this is true? So this is by monotonicity. Why the second inequality is true. This is an example of things that people do like in advanced probability, this, they write these inequalities. Why is this true? This is really another instance of an inequality that holds always. So this, if this is true, then I can take the expectation of both sides and I get that expectation of this is less than the expectation of that. And then because A is constant, A comes out. So I really need, so this would be linearity. This would be monotonicity. So why this is true? Why is that true? Again, you consider the two cases, right? So either X is bigger than or equal to A, in which case this just says X is bigger than or equal to A, which is true. Or X is less than A, both sides will be 0, so it's still true. Okay, so this is true, then you take the expectation. So intuitively, what I'm doing here is like valid because I'm, like, you can see intuitively under this indicator, this is going to be bigger than or equal to A always. So I can replace it with something which is smaller, and this comes out. So intuitively, because this indicator, whenever this indicator is active, this is going to be at least A by assumption, so this comes out. Once you get comfortable, you don't have to write this little argument here. Yes, I see Aaron is also mentioning this. X is bigger than or equal to A. Yeah, or 0 bigger than or equal. Yeah, exactly. So this star is true that way, and then you take the expectation. Or if you, once you get comfortable, you just say, okay, under this indicator, this is at least A. I can replace it with A and comes out. But this really, if you want to be really careful, this is the whole argument and the other side. Okay, now, what can I say about this? What is the expectation of the indicator variable, if anyone remembers? An indicator variable takes two values. So what is its expectation? Let me hide the end result. What is the expectation of the indicator? Let's see how many people remember from one of the earlier lectures. Or you can just compute it. Yes, so it's just going to be the probability of that event. It just takes two values, 0 or 1. It takes probability 1 sorry, value 1 with the probability of that holding is just the probability of this event, and then the other one doesn't matter because you get 0 times the probability, whatever it is. So you get that. Okay, so we proved that expectation of x is bigger than or equal to a times the probability of x bigger than or equal to a. Since a is positive, I can divide both sides. I get by a, I get this. Okay. Or if you rearrange it in the other way, we really have shown that this is less than or equal to expectation of x divided by a. Okay, so this is in general true. The only assumption is that the x is non-negative, a non-negative random variable. It doesn't take negative values at all. The probability is really probability that x is bigger than or equal to 0 has to be 1. Another way of saying is that x bigger than or equal to 0 almost surely. They write it like this. Always. Always in probability is just doesn't have to be always. Like there could be some samples, like some elements of the sample space in which it's negative, but there should be no probabilities there. So all the possible outcomes and all the possible outcomes, they have to be non-negative. So this doesn't require any density or any kind of variance, independence, nothing, right? So we didn't use density. It works for discrete variables, it works for continuous variables, it works for mixed variables that we haven't even seen. Like we have seen examples where they don't have density. So like the joint distribution. There's things that don't have like typical density in the sense that we discussed. But this holds because it just follows from the monotonicity, and monotonicity is true always. So expectation is always a monotone linear operator. Doesn't matter what the underlying measure is. And so this is very general. Inequality is very general and just uses basic properties of expectation and the fact that the expectation indicator is the probability of that event. Okay. So this inequality is also sharp in the sense that there are cases where this holds with equality. Okay, so you can see here. So you have a non-negative waiting time. So W is waiting for something and it's random, mean is 10. Markov inequality tells you this bound. So what is the chance that I have to wait like more than 50 minutes? So Markov inequality tells you that if the expectation is 10, this would be 10 divided by 50. So it's like 0.2. There's like 20% chance that you have to wait more than 50. Does it mean that you're assuming anything about the distribution of W? It doesn't. So it holds always. At least, like at most you're like the probability that you have to wait at least 50 is at most 20%. Okay, this is true always. For certain distribution, it could be less, but there are distributions for which this holds. So for example, you can construct this distribution. 80% of the time you don't wait anything, like 0, just instantly, like do whatever needs to be done. And 20% of the time you wait 50 minutes. Okay, this is a binary variable, takes two values, and you can easily see that the expectation is like 0 times this plus this times that. 50 times this would be 10, right? And so this random variable has expectation 10, and the probability that this is bigger than or equal to 50 is really exactly this probability, right? So this Markov inequality is tight in general. You can't improve it. There are distribution or random variables for which this holds as equality. If you know more, let's say if you know, for example, that W has an exponential distribution, then you can do better. The tail is like going down much faster. In particular, for example, if you know that the variance of W is like a certain value, you could do better, and so on. We'll see. Okay. It can be loose for a particular distribution, but no uniformly smaller bound follows from the mean alone. If you just know the mean, this is the best you can do. If you know higher order moments, you could do better, potentially have a tighter bound. Any question about the Markov? It's the fundamental. It's called sort of a tail bound. It's called a tail bound because this is like a tail of a distribution. As I mentioned, this is like it calculates the probability that you lie on this one-side interval. It's like the tail of the density or distribution. Like measures like how much mass is in the tail. questions about Markov. It's one of the fundamental inequalities, and a lot of other inequalities follow from this. And we need these inequalities to be able to control the probability of that central event that we wanted. Questions? Okay, so inequality is if and only if. It's a good question. So this is an example where uh, it's a good question. So Arun is asking, is inequality if and only if P of x is equal to 0 plus P of x a is 1? It's like basically taking two values. I don't know. It's a good question. Let's think about it. Can you come up with an example where this is equality and it's like this is a 2-point mass like distribution, but let's say it's a 3-point mass that achieves equality. You may probably ask ChatGPT, potentially knows. I have to think about it. It's a good question. So is there any other distribution for which we have equality? It's a very good question. Can there be for example, a 3-point distribution that achieves the equality? Let's think about it. Okay, any other questions? No other question. So building on Markov, you can prove another very famous inequality, which is called Chebyshev inequality. Okay, and this holds for a general random variable doesn't have to be non-negative. It just has to have mean and the variance. We really didn't talk about existence, but you really need this to be finite and also the second moment to be finite for the mean and the variance to exist. There are certain variables for which this integral is not finite, and so they don't have a mean. Or this is finite, but the square doesn't make sense. So you need this for the variance, the second moment. It will be infinite. But if you have finite, for most of the things that we look at, the mean and the variance are finite. If you have finite mean and variance, then you can form this deviation squared. So x minus mu squared. This is going to be a non-negative variable. This is like y, right? I can apply Markov to this. I can apply p of y bigger than, rather than looking at a, I can say a squared. A squared is going to be non-negative. And if y is equal to x minus mu squared, this is always going to be non-negative as well. So I can apply Markov to this. I get expectation of y um, divided by a squared. Okay, and a could be positive or negative. But a squared is always non-negative. So I can apply Markov like this to y and a squared. And this side is really x minus mu squared bigger than a squared. And um, let's say a is positive, or actually a non-negative, because I want to take the square root. We're going to assume this doesn't matter. So this is the same as that, and so this is equivalent to that, and then this is equivalent to the absolute value. If I take the square root of both sides, this is equivalent to this. Okay, the square is bigger than square of a squared if this is true, and this side would be just the expectation of x minus mu squared, and this is really the definition of the variance. Okay, so what do we get in the end? We get the probability that x minus mu is bigger than or equal to a is less than or equal to the variance divided by a squared. Or you can say variance of x divided by x squared. Right, so that's the inequality. This is called the Chebyshev inequality. And you can see it's kind of better in a sense because it's divided by a squared. This was divided by a. So for example, in this case, if what like you look at the 50, deviating from like if the mean was 10 and x minus this is bigger than 50, this would be variance divided by a squared. So if the variance is small, this is going to be much smaller. In general, it goes down like 1 over a squared, which is faster than 1 over a. So that's the Chebyshev inequality. It holds for any random variable. it characterizes the deviations around the mean in absolute value, which would be a non-negative variable. Okay. Um, you could have done it with this. You could have had a Markov inequality like this. This is also non-negative. You could have done this less than or equal to the expectation. This is going to be an absolute value. This is like an absolute first moment. This is also true. But this is in general better for large A um, if the variance exists. It goes down like 1 over A squared. This goes down like 1 over A. And this is going down faster. Second order polynomial. So this is saying that a random variable that has a finite variance, the tail has to go down at least this fast. Go down faster than a general random variable. And in general, if you have higher moments, you could apply like power 4 here, that you get the fourth moment here, and then you get the power 4, so it even goes faster. But let's not worry about it. So this is Chebyshev. Any questions? It's just an application of Markov to the squared deviation. Okay. And this side, instead of the expectation, you get the variance, which is the expectation of the underlying deviation squared. Okay. Questions? So let's see what we have on the next slide. Right. So another way of writing this is you can apply it with k times sigma. Right? If I apply it with k times sigma here, you get sigma squared divided by k sigma squared, k squared, sigma squared, and sigma squares cancel, you get k squared. So this side's kind of invariant to the variance. Now this is saying if I have k multiple of sigma, how likely is it that basically x is k times sigma away from the mean? And the answer would be in general 1 over k squared. Okay, so let's say if we have 2 here, then you get 1 over 2 to the 2, which is 1/4, right? 25%. And you know, for example, for normal, this is much better. So this is saying like 75% of the time, you are within minus 2 sigma and 2 sigma of the mean. This is for a general distribution, but for normal, for example, you get like 90, I forgot, 95% or 97%, maybe 95% chance of being within 2 sigma of the mean. Okay, but this Chebyshev is general. So there are distributions for which this is tight as well. Um, okay, let's see an example. So can you do this example rather quickly? Let's see if people can. So a random variable has means 100 and a standard deviation 15 without assuming any distribution. Can you find a lower bound for this probability? Maybe think a little bit about this. Can we use one of these inequalities to find a lower bound? Anyone? Comments, questions? Clear? Can you, what is the first step, for example? Sorry. I can do x minus 100 between negative 30 and 30, right? So this is a probability that absolute value x minus 100 is less than 30. Okay, which is going to be 1 minus the probability that x minus 100 is bigger than or equal to 30, right? Now what can we do? Can we use Chebyshev? What does Chebyshev say? Hang on, just apply the Chebyshev inequality, right? A would be 30, sigma squared is 15 squared divided by 30. Right, so this is less than or equal to that, so 1 minus this would be bigger than or equal to 1 minus 15 divided by 30. So we get 15 here, and then did I make a mistake here? Oh, yes, read that. It shouldn't be negative, hopefully. So you get 15 divided by 30 squared. Get 1 minus 1 to the 2 is like 0.75. Or you could have just used this version. Right, so this is like 30 is 2 times the standard deviation. So you really get 75%. Yes, Hayden is correct. It's like it's an upper bound basically. So the tail is upper bounded, but this is like the bulk. So this is the opposite. So you get 1 minus this. So uh, the opposite event would have like 1 minus this, so the inequality is reversed. So it's going to be bigger than or equal to 3 over 4. 75% guaranteed. Okay. It doesn't mean that the probability is equal to this, but is at least this much without any more assumption. For a particular distribution, could be more. So, any questions? So you can use these to get crude estimates, and there are certain distributions for which this holds. If you don't want to make any assumptions, if I just give you the mean and the standard deviation, you can tell me like lower bounds or upper bounds and these events. So does this conclude that there is a probability of at least? Yes, yes. So this is saying this is a lower bound. So what it's saying is that the probability that x lands in this interval is at least 75%. It could be more for the actual distribution, but without knowing anything, you can just guarantee this. You just know the mean and the standard deviation is guaranteed to that this much mass has to be there, which is pretty amazing. You didn't need to do any like integration or anything. We don't have any density or anything to actually do it, but this is really saying these constraints and the fact that this has like follows the probability law enforces this probability to be at least 3 over 4. It's really an interesting, amazing thing if you think about it. Just for normal, for example, it could be like, as I mentioned, it would be much higher. This is an example where you're 2 sigma squared, 2 sigma away from the mean, or basically within 2 sigma of the mean. For normal, for example, this would be like 95%. But this is saying for any distribution, doesn't matter. You don't need to assume. As long as the variance exists and the mean exists, then you have that. Any more questions about this? Okay, so they are interesting on their own right. Markov and Chebyshev allows you to bound certain probabilities. And because they're so general, they allow us to prove general results. So this we can go back now to the average. So we have IID xi's, mean mu, variance sigma squared, and then we form the average and we look at the variance, we know the variance is sigma squared n. Okay, we also know that the mean, the expectation, the mean is mu. Now I can use exactly the Chebyshev. I know these two pieces of information. I don't know anything else, but that's enough. I'm going to apply the Chebyshev says x bar n minus the expectation of x bar n, which happens to be mu, bigger than epsilon is less than or equal to the variance. So it's really, if I want to write it properly, this is like this minus its expectation. This is always true. This is the Chebyshev, less than or equal to the variance of x bar n divided by epsilon squared. Okay, but this variance happens to be sigma squared over n. So when I just simplify, I get this. Okay, so this is the form. So you can see the n appears here. And this comes from this. Okay, now we easily see that as n goes to infinity, this side is going to 0. So this probability is going to 0. Right? Another way, like finite version, is if I want to make this to be like less than delta, how large the sample size should be. Okay, and if you rearrange, this is give you just sigma squared has to be less than or equal to n epsilon delta, and then n has to be bigger than or equal to sigma squared divided by delta epsilon squared. So it has to be this much. So for any epsilon you fix and any delta, you can find the size of the samples such that this probably is not a delta. Okay. So if you like change the epsilon, you can see a square. So the dependence is delta here and epsilon squared. So if you change the tolerance by a factor of 2, then you'd need like 4 times more. So if you want to be closer, like whatever interval you were, you want to like half the interval, half the length of the interval, then you need 4 times more. So, okay. So this implies, I don't know if you have it on the slide, but this is, let's see if you have it somewhere. Yeah, so let me go back later. So uh, just another couple of slides, we formally state the law of large numbers. But is this clear? You could do like finite sample analysis if you want to see how close the mean is to the mu, or like if you want to guarantee, you can compute the sample size needed. This doesn't require any distributional assumption. If you have Gaussian, you get a much better. But in fact, for Gaussians, so give me a second. Um, right. Yes, sorry. Um, okay, so sorry, let me yes. Okay, sorry. So let's do another example. So suppose I toss a fair coin 400 times, and I'm gonna have an estimate of the probability by looking at the average. Okay, so the so imagine xi's are Bernoulli p. It's like the probability, like so if it's like xi is like 1, if I observe heads, for example, and 0 if I observe tail, or whichever you want to pick. This is probability p, this is probability 1 minus p. So this is a Bernoulli trial, and their IID. If I look at the average really is an estimator of p. So you can call it p hat. Okay, this is an example where you now see a bit of statistics. So p hat, this we can consider it an estimate. It's like the um, um, how many times you observe heads divided by a total, right? That's the typical way of estimating the probability. It's like a frequentist estimator. So we know that the expectation, let's say this is a fair coin, so p is really 1/2. So the expectation is 1/2, and we know the variance. So like this is going to be, so how do we compute the variance? Anyone remembers how this comes out to be? The mean we already know, but the variance is, how do we know this? Anyone knows how this comes out? Think a little bit, see if you can. Anyone remembers the resulting formula? So Arun is saying it's n times p times 1 minus p for variance of x, then over n squared. Yes. You can think of it as either the sum. So the sum is really Bernoulli. Sorry, the sum is binomial, right? And so the variance of the sum would be n times p times 1 minus p. And then the variance of x bar, which is p hat, would be 1 over n squared times this. Okay, you get p times 1 minus p divided by n. Another way of saying it is that this is really an average, so variance of p hat would be variance of one of these guys, let's say x1, divided by n. We know that it's just like this, and the variance of one of them is, variance of x1 is a Bernoulli variable. We have calculated this before. It's going to be p times 1 minus p. Okay. So this is going to be 1/2 times 1/2, which is like 1/4. N is 400, so I get this, right? Questions? Does it make sense? Okay, so now I can use, for example, my Chebyshev inequality. So p hat minus the expectation, let's say bigger than 0.1, is less than or equal to the variance, which is this guy, divided by that. And that would give me like, hopefully this, right? 1 over 16. And so you can compare this estimate with the actual value here. Okay, so the actual value would be uh, this. So why is this the actual value? So p hat is really Sn divided by n, and Sn is binomial n and p, right? So you just plug in here and then multiply. So this event is really Sn minus n over 2, bigger than or equal to 0.1 times n, right? So this would be Sn minus 200. That's n is 400, bigger than or equal to 40, right? So this probability, you have to like roughly, let's say it's twice because it's going to be symmetric. This is a little bit approximation. Uh, but whether it's exact, I'll let you figure it out. But so this is saying basically Sn is either bigger than 160 or less than, um, sorry, it's less than 160 or bigger than. Um, the way that it works is like either bigger than 240 or less than 160. Is it exactly or approximately? I'll let you think about it, but most likely exact. But uh, what like the probabilities are going to be the same because kind of a symmetry. So let's say if you believe that, it would be twice the probability that this less than. So this is like 200 is mean. This is saying you're above or below, either below this much or above this much. And so the mass that you put here would be equal. I forgot if it's exactly equal or approximately equal, but that's, I'll let you figure it out. And then this one is really a sum, right? So it's just summation from 0 to to 160 binomial like distribution, right? This is like the probability that Sn is k, and this is like n choose k divided by times p to the k 1 minus p to the n minus k. Okay, p is the same, so you get 1/2 to the k times 1/2 to the n minus k. So this just simplifies to 1/2 to the n. And so you get this part, 2 to the negative 400, that's 1/2. And then this is just 400, choose k. And so you just have to compute this sum, and if this is correct, this would be that much. It's much better. Okay, so the concentration here is much, much better than what Chebyshev predicts. And in fact, this is a result that it's like a concentration would be exponential. It's like not really going down like this, but it's really going down like e to the negative some constant times 1/2 squared. Um, Rather than polynomial. This is a concept that kind of CLT is going to be suggestive, but in a higher course, you actually can prove a much better bound. It's an exponential concentration bound. So in a later course, like a higher order, like if you take a graduate course, you prove that for this case, for binomial. And this is an example of a sub-Gaussian, general sub-Gaussian random variable. We don't need to worry about it, but for these things, an exponential tail-bound holds. That would be much closer to the actual value. Okay, you can see like there are many, many more zeros than what this predicts. Okay, so Chebyshev is good, but in certain cases, like a fair coin toss, it's like a very conservative upper bound on the tail. You get a much better like exponential bound if you do. If you're interested, you can check Hafting inequality. Hafting inequality. That's an example of exponential. And for this particular case, it's even better versions. Okay, any questions? This is an example where uh, this is kind of not always sharp. And in a lot of interesting cases, the concentration is much, much, much stronger, like exponential or quadratic rather than 1 over a quadratic. Questions? So do this calculation. I mean, this one you can't, but you can like, just confirm for yourself that this is the right quantity, and then you calculate it on a computer, ideally. And just verify this. I hope this is correct. So let's go back to this bound, right? This is the bound that we have for a general average of a general IID sequence. So what happens is easily we can see that this goes to zero as n goes to infinity for any fixed epsilon, okay? And this is stated in like jargon as x bar and converges to mu in probability. What it means is exactly this, that this quantity is like this probability that x bar n minus the limit, in this case mu, the absolute value is bigger than epsilon, is going to zero for any epsilon, okay? So what we proved really is this sort of notion of convergence in probability. Basically, the probability of any fixed size error around this limit is going to zero. Okay, this is called convergence probability. The key is like the independence and IID-ness. Basically, sorry, identically distributed. The identically distributed part is not severe, but the independence is really needed. Okay, so you can easily extend it to the case where they're not identically distributed, but they're independent. And what you in that case need is like, you can easily see that in that case, if the variances are different, then this is replaced by this. Sorry, by something like this. So you get basically 1 over n times 1 over n summation I from 1 to n. And so you get the average of variance. So if this is converges to something, then it would be similar. So as long as uh, the average variances that converge to something, you have the same result. So the identically distributed part is not important. Actually, this the first I is independence. Independent is important. Identically distributed is not much. So is this statement clear? So the meaning of this notation is exactly that this goes to zero for any fixed epsilon. Fix any epsilon, this goes to zero. What this is saying is like basically you put more and more mass, probability mass around mu. Roughly speaking, this is kind of the picture. So suppose the xi's are exponential, they're independent. And then in this case, exponential 1, the mean would be 1, the variance would be 1. You can verify. So if this was lambda, this would be 1 over lambda. This, I believe, is 1 over lambda squared or something like that. And then, so if you look at this, this is the exponential, single exponential. So the average when n is equal to 1. The, sorry, this is the one. You can see like this is the density as at n equal 1. This is the density at n equal 5, and this is the density at n equal 25. And you can see if I look at the fixed interval, this is a fixed interval, this shaded area is like capturing that interval. If I look at the fixed interval around the mean, more probability. So the area under this curve is the probability that x bar n for n25 is in that interval. And this is much bigger than the mass under the other one, right? You can see the mass under this original one is less than the mass under the orange, let's say, curve, and it's less than, much less than the mass under the green curve. So that's the idea. The concentration is kind of captured by the probability mass basically shifting more and more into that interval compared to yeah, compared to the early parts. Yeah, so this is like a band is like this. Okay. So there's a bit of right skewness here. So this doesn't tell you about the shape. So what is the shape of this? The shape in this case would be, anyone knows what the summation would look like, or like what the distribution? So this sum you can actually, the sum of a bunch of independent IID, basically exponential random variables. There it has like a name. The distribution has a name. Anyone knows? This would be gamma distributed. distribution. We didn't talk much about it, but uh, it's not going to be normal because they're exponential. They're one-sided. So the sum of independent would be exponential, but you can actually see, and this is after you normalize. So if I look at Sn, um, if you normalize it, then it's not going to be gamma in that case, but you can compute the density. The density of this is clear. You can check in Wikipedia. Uh, and then Sn over n is just the rescaling. We didn't talk about transformation much, but you can actually evaluate the density and just plot it. Um, it turns out that something it starts to look like normal, but the thing that looks like normal is, we'll see. If you look at Sn, or sorry, x bar n, this is x bar n, and then subtract the mean, um, and then this is going to kind of zero in a sense. The probability that this is, like you can see, like roughly is saying that distance is the difference is going to zero. But it turns out that if you normalize it, there's a right way of normalizing it. If I normalize it by something, then that would stabilize. Then the distribution of this thing is going to converge to a Gaussian. And that's kind of the shape that starts to appear. We'll see that later. This is the second limit theorem, which is the CLT, which is a more complicated, not complicated, but like a more subtle issue. Okay, so to wrap up, so what the weak law says is choose any fixed epsilon. Uh, and the chance that x bar n kind of misses mu by that amount goes to zero in probability. Um, and then a finite n version you can get by like a Chebyshev. You can get like how large n has to be for you have a tolerance of probability. It doesn't say that x bar n is equal to mu. It doesn't say what happens to individual observations or like individual um, yeah, the individual xi's are not getting less variable. And also, technically, the weak law doesn't tell you about a particular trajectory. So what happens for one sample? There's a like strong law of large numbers shows that this converges for almost all possible outcomes. And also, I mean, we don't worry about that. But the weak law doesn't say the shape of the remaining fluctuation. There is a bit of fluctuation, which is really what is remaining. So if I look at the distance of x bar n minus mu, this is going to zero. But if I do a root n rescaling, we'll see later that this is stabilizes. There is a random fluctuation around mu at this scale. Basically, it's saying um, it's going to zero, but there's randomness in it, and we can like, capture the randomness at the proper scale. If you rescale it properly, then this stabilizes. Um, okay, let's do one more thing here. We have 2 minutes. Uh, if you imagine like if you do an experiment and let A be an event, so you do the experiment many times, and then we look at the indicator that the event A occurs at trial I. You can look at it as an indicator. Okay, this is an example of the Bernoulli case. The probability of this indicator would be just the probability of that event. Okay, P would be the probability of A. And so the indicator that I defined this way would be a Bernoulli random variable probability P. Then the average, this is like the frequency, like empirical frequency. I did this n times, and each time I record whether A occurred or not, event A occurred or not, and this is like telling you the empirical frequency of that happening, basically the number of occurrences of A divided by n. And by the law of large number, this has to converge in probability. Now we know like to probability of A because that's the expectation. Okay, so the weak law of large number tells you this converges to probability. Each one of them have like expectation this, variance this, and then basically it's an example of the weak law of large numbers for the Bernoulli values. Okay, so this is kind of captures the idea that long run frequencies converge to probability. It's like the frequentist interpretation of probability, but it is realized inside the model. We didn't assume that this is the meaning of probability, right? You're just saying, okay, you start with the um, axioms of probability, And then we can prove inside the probability model that now so the meaning of this is whatever you want, but if I now have independent repetitions of the experiment, and if I define this indicator as that event, like an event happened at trial I, I can say these are now independent by kind of, we have a formal definition of independence. If we have independent trials, it means that these are independent. And then if I look at their average, this is basically the frequency of occurrence of that event. And so that would converge to the probability. So this is a very nice kind of conclusion within the theory of the kind of frequentist idea. It's like kind of a bit hard to wrap your head around it because intuitively we view probabilities as meaning frequentist idea. Like if you're frequentist, that's what your intuition. But we can make that intuition precise inside the theory as well. Once you define independence, then we have this law of large numbers that kind of formalizes that in this sense. So that gives you a very nice view of frequentist probability as an example of the weak law of large numbers. Okay, questions about any of this? So I wanted to talk about this. We'll talk about the Monte Carlo. Yet another application of this weak law in law of numbers is to approximating integrals and interesting like things. This is the remaining material we'll talk in next lecture, and then talk about the CLT in the following lecture as well. Okay, questions, comments? I'm gonna stop here. Questions? Okay, if no questions, thank you guys. See you next Monday.